Here we're told to find the directional derivative of the following function at the given point and in direction of the given vector. Our function of x and y is x squared y plus xy cubed plus 4. Now, at the given point here is 2, 3. And the vector that we have is square root of 2i plus 4 over 7j. This vector could also have been given as square root of 2, 4 over 7, right? Remember the different forms you can have your vector. Alright, so remember now, the directional derivative sometimes it's written as d of u of f. F is the function and d u. U is considered as the vector, right? The directional derivative in the direction of that vector u. Now, the formula here is written this way, right? Now the thing is, this upside down triangle f, you remember, means the gradient of the vector that we're given, and the u, I underline the u means the unit vector. You want to find the gradient function, the gradient vector for our function and multiply it by a certain value. But you have to multiply it by the unit vector. Why? It's because you don't really want to change the value of the gradient vector. It's like when you had, let's say, 5 over 7 plus 3 divided by 14, and you wanted common denominators. This 5 over 7, you multiply it by 2 over 2, because you want 7 by 2, something over 14. It would, 5 over 7 would be like 10 over 2, 10 over 14, right? 5/7 would be like 10/14. But you don't want to change the value of 5/7. So you multiply it by 1. But this, you know, is 1. So you multiply any number by 2 over 2, you get back the same value. It looks different, but it's the same value. Multiply it by 3 over 3, right? Same value. So in this case, you have this time the unit vector. 2 over 2, 3 over 3, 4 over 4, 5 over 5, 6 over 6, whatever number over the same number is the unit number, unity, which is 1. And if you multiply that by any other number, the value of it does not change. The value of the number doesn't change. Same argument here. Alright? Multiply a vector by a unit vector. The dot product by a unit vector. It looks different, but the value doesn't change. So you can apply the same argument to this. So now, here, this gradient vector, the function, is equal to, it's going to be delta f by delta x. Well, I should use the angle bracket because it's a vector. Delta f by delta x, delta f by delta y. Same thing as if I had said delta f by delta xi plus delta f by delta y j. You remember the different ways how you can write down vectors, right? So, here now, what you have is delta f by delta x is what? Delta f by delta x. And by the way, what you do, you see, pause the video and work it out. And then we'll come back to it. Okay, have you finished? Now, here, you want to find the the derivative here. Partial derivative of f with respect to x is going to be what? 2xy plus y cubed. See that? Then the partial derivative of f with respect to y would be x squared plus 3xy squared. Ensure that you carefully examine that and verify that those are the derivatives. Alright? So, what you have is that the gradient vector f is 2xy plus y cubed I plus x squared plus 3xy squared j. Right? So you have that. Some noise you're hearing there. Going after mosquito with my zapper. Alright, so we'll come back to it. Now, what happened at the point? We need to find this gradient at the point 2, 3. Now, at 2, 3, you're going to substitute 2 for x and 3 for y and work these out. So, the gradient of f is good. Alright, let's not jump to that. Let's do it one at a time. The gradient, the partial derivative of f with respect to x at 2, 3 is equal to 2 times 2 times 3 plus 3 cubed. So what you do is that you substitute the values, right, into the particular derivative. So that's what you do there. So now, when you work this out, what do you get? 2 by 2 is 4, 4 3 is 12, 12 plus 3 3 is 9, and 3 is 27. Right? I'm going to be using my calculator offline, right? Off the air. So, what I have here is 12 plus 27 giving 39 is equal to 39. Alright? And then, by the way, remember, if you're looking online for examples, sometimes they don't put the at, they just say delta f by delta x and this in bracket, or fx, the other notation here. Sometimes you will see that, but the same thing. Delta f by delta y at 2, 3. What is it? Well, you have x squared. X is 2, so it's 2 squared plus 3 times 2 times. Y is 3, so it's 3 squared. So you have 4 plus 3 3 is 9. 9 2 is 18. 18 times 3 gives us 54. So then 54 plus 4 is 58. So there you have that. So the gradient vector is 39i plus 58j. Alright? Now, here, the next thing is to find the unit vector in direction of the unit vector. You have square root of 2i plus 4 over 7j. So our vector, right, is square root of 2i plus 4 over 7j. Now remember, the unit vector is going to be the vector divided by its magnitude. So what you can say here is that if I write the unit vector, right, with a line over it, if I was typing it, it would be in bold. So the unit vector is equal to our vector divided by the magnitude of the vector, right, is equal to, well, let's find the magnitude one at a time. What's the magnitude of this vector? Well, it is the square root of, now remember where it comes from. Like Pythagoras theorem, this is I-axis. Oh no, this is the I-axis. Oh my, why it disappeared? This is the I-axis and this is the J-axis. X and Y. The size of this vector is the square root of 2, and the size of this vector is 4 over 7. Alright? So here now, we have a right angle triangle. This is a hypotenuse. So this is square root of this side square root of 2 squared plus this other side square, 4 over 7 squared. So that's where, just a reminder that that is where the thing there, the equation comes from. So we're going to have square root of 2 squared. So you see the length of the hypotenuse, this square and the length of the hypotenuse. Alright, let me do it this way. Remember what Pythagoras theorem says is that the square on the hypotenuse is equal to the sum of the square on the other two sides. So it's the other one on the other side squared plus the next side squared. Alright? So that is going to be square root of 2 squared is 2 plus 4 squared is 16 over 7 squared, 49. So what you have is that the magnitude of the vector is therefore the square root of 2 plus 16 over 49. Alright? So what would this amount to? Square root of, now if you work it out as a fraction, you could work it out as decimal, but for neatness let's keep it as a fraction. I use my fraction calculator instead of spending a lot of time working it out here. 2 plus 16 divided by 49. So 2 plus 16 divided by 49 equal, what I have is 114 over 49. Alright? 114 over 49. But just for neatness and so on and so forth, let's just keep it, let's just write it as a decimal to 3 decimal places. 2.327. So it is square root of 2.327. So you see that 2 plus 16 over 49 is 2.327. What's the square root of that? 1.525. So it is 1.525. So now, here, that's the magnitude. So therefore, the unit vector, alright, bold U, alright, a U with the line under it, is equal to the original vector, square root of 2i, plus 4 over 7j, divided by 1.525. Let's write it as the square root of 2 over 1.525i plus 4 over 7 over 1.525j. Now, let's say that the unit vector is equal to, let's put the square root of 2 over 1.525. I use my calculator of the here, and it's the square root of 2 divided by 1.525 equals, I get 0.927. So 0.927i. And remember, I'm keeping to 3 decimal places for accuracy, right? Practice to keep to at least 3 decimal places, and then when you're done with the question, you can round off to whichever number of decimal places or significant figures you want. Alright, so the next thing, 4 divided by 7, and then that over 1.525 equal 0.375. 0.375j. So that is our unit vector. Now we want the dot product here. So the directional derivative of the function duf, so is equal to the unit vector 0.927i plus 0.375j dot, and then what we have is, oh, I had it up here as the gradient vector first. Let's just be consistent and do that. We're going to have this second, so let's put the unit vector second. So the gradient vector is, what was it again? 39i plus 58j. So it is 39i plus 58j dot that. Alright? So directional derivative here, remember how to calculate the dot product. Alright? It's going to be 39 times 0.927, and remember the dot product is a scalar, it won't be a vector. Remember the I and the j are just showing the directions, so you can drop them off now. Right? So it's 39 times 0.927 plus, and then 58 times this I by I, j by j. 58 times 0.375. So that's what you have there. And then what would that come after? Going to be 39 times 0.927 equal 36.153 plus 58 times 0.375 equal 21.75. And what will all that amount to? When you add 36.153 to 21.75, have 36.153 plus 21.75 equal 57.9. Well, it's 57.903, but now that is the answer. I can just round it off to 57.9. So that is the directional derivative of our vector. All right. So remember now, of our function, I should say. So remember now, you have the function. Directional derivative going to show you the derivative of the function at the point in the direction of the unit vector. So it's going to be the gradient vector for the function, the dot product between that and the unit vector. So you find the gradient vector, just find the gradient function, the partially of each variable. You find the partial derivative of x with respect to x and the partial derivative of the function f with respect to y. Substitute the point that you're given into it. So you would have found the gradient, the vector, upside down triangle, right? And then you find the unit vector of that other vector, that in the direction of that vector, you find the unit vector of it. So you divide it by its magnitude, find the magnitude and divide it by its magnitude, right? And then you find the dot product. The dot product is like you're multiplying it. So you use the unit vector, because the argument here is that if you multiply a number by 1, you get the same number. Number is the 1 is the unit number. In this case, we're dealing with vectors, and therefore the unit vector, right, is like 1 in numbers. So you don't want to change the original vector, so it's the unit vector you multiply it by. Alright, so that will be it for now. I will see you in the next video.